All right, we're going to look at the Walls Matrix Factorization notebook. We're going to go through collaborative filtering using Google Analytics data. So we're going to see how we can do this to work. So first what we're going to do is we're going to import our OS library here, and we're going to set our project, our bucket, and our region into our environment variables. Replace these with whatever your project ID is and your bucket name. We're going to put these in our environment variables right here. We're using TensorFlow version 1.8 in this lab. And then we're going to set our configs for our project and our compute region using those environment variables by calling bash. From there, we're going to import TensorFlow because we'll be using that for this lab. And we're going to print the TF version just to make sure that we're using the right one, 1.8. All right, so now we're going to create our raw data set. So for collaborative filtering, we don't need to know anything about either the users or the content. We essentially, all we need to know is the user ID, the item ID, and the rating that the particular user gave the particular item. This is what makes the user-item interaction matrix. In this case, we are working with newspaper articles. The company doesn't ask their users to rate the articles. However, we can use the time spent on the page as a proxy for rating, which is going to be their session duration. Normally, we'd also add a time filter to this, for instance, like the last 7 days, but our data set is itself limited to a few days, so we don't have to worry about that too much. All right. First, what we're going to do is we're going to import the BigQuery library from Data Lab. Then we're going to write our query. In our query, we're going to be using standard SQL, and we're going to create a CTE table here with this with visitor page content. And we're going to select from the table right here, GA session sample, the full visitor ID. And then we're also going to select the max from this index from this nested table on the custom dimensions, which these are going to become our content IDs. Okay, this is the latest content ID. And then we're going to take the lead of the hits time, and we're going to partition over the full visitor ID, and we're going to order it by the hits time in ascending order, and we're going to subtract out the hits time. And this will be our session duration. So basically, each session that a user interacted with that content. What we're going to do is we're going to make sure that we're only including hits on pages. So that's why we're going to have this where clause here with hits.type equals page. And then we're going to group by the full visitor ID, the latest content ID, and the hits time. From there, using the CTE table, we're going to select the full visitor ID as the visitor ID, the latest content ID as our content ID, and the sum of the session durations as our session duration for that particular visitor ID and content ID. Okay. We're going to filter out things where the latest ID is not null because we don't really care about content that doesn't exist. And we're going to group by the full visitor ID and the latest content ID. And we're going to make sure that session durations are greater than 0. Because anything that's 0 or less than is either bad data or not useful for us. And I'm going to order by the latest content ID so that it's repeatable. All right, so now that we've had that SQL query written, we're going to write that into a data frame. We're going to do this using the BigQuery library, where we call BigQuery, the query we pass, which is our SQL query we created up here called SQL. We're going to execute it. We're going to take that result and send it to a data frame. From there, we're going to print off the head of the data frame, which will show the first 5 rows. As you can see in our little table here, for this row, we have this visitor ID, which is a long integer, a content ID here, the thing that they viewed. It's another long integer, and then the session duration right here, which is going to be how long that visitor interacted with this piece of content. Let's see some of the stats. So to do the stats, we're going to do a df.describe. So this will describe the statistics of the data frame, and then we're going to print it out. As you can see here, we have our counts and our session durations. So we have, on average, it looks like session durations of 1.2 times 10 to the 5th seconds. And there's 2.7 times 10 to the 5th number of interactions. See, standard deviation here is pretty high, so that way you can see there's a lot of variance amongst users. The minimum looks like it's 1 second. Well, why would it be 1 second? Well, remember, we filtered out anything that was 0 or less, so therefore we shouldn't have anything less than 1. And their maximum here, that's a long time. Someone's really reading a lot of content. It looks like 7.6 million seconds. All right, but let's try to get that in more reasonable ranges. To do that, we're going to create a rating. And the rating is going to be the session duration scaled to be in the range of 0 to 1. This will help during training. To do this, we're first going to take our session duration, and we're going to subtract out the stats of the median for that session duration. And we're going to divide by the median too to normalize it. From there, we're going to add 1 and multiply by 0.3 to get our new rating. From there, we're going to say if any ratings are greater than 1, we're going to cap it at 1. So therefore, nothing can be higher than 1. And now if we do a df.describe, you'll see we still have the same number of counts. However, our ratings all have the correct ranges. You see the minimum here is almost 0, and the maximum here is 1, where we've capped things off that nothing can ever go above that. So now we don't need session duration anymore since we've created our own rating column, so we can delete it from the data frame. Next, we'll call bash, and we'll make sure that anything in our folder called data is deleted, and then we'll make a new directory called data that we'll put all these pieces of data in. To do that, we're going to call the method to the data frame toCSV, pass in it our CSV name we want to create, collab raw, so basically our collaborative raw data. Make sure there's no index and no header. Then we're going to call bash again, and we're going to write it out. And as you can see, there it is. As you can see, here's our visitor IDs, our content IDs, and our ratings that we just created, all going from 0 to 1. Great. So now what we need to do is we need to create our data set for walls. The raw data set above won't work for walls. First, the user ID and item ID have to be 0, 1, 2. So we need to create a mapping from visitor ID in the raw data to user ID and content ID in the raw data to item ID. Why do we do this? Well, remember, this is a user-item interaction matrix, and we need to have the indices of the matrices to be able to link up later on. We also need to save the above mapping to a file, because at prediction time, we'll need to know how to map the content ID in the table above to the item ID. And same goes for the users. We don't know who user 0 is going to be, or item ID number 462. But if we have the reverse mapping, we can also go backwards and say, it's actually user really long integer that goes to content ID, also long integer. But that fits our business case. Lastly, we'll need to have two files, a rows data set where all the items for a particular user are listed, and a columns data set where all the users for a particular item are listed. Remember, we're using alternating least squares here. So we go back and forth between rows and columns, fixing one while solving for the other, and vice versa. All right, so to create this mapping, I'm going to import pandas and NumPy. I'm going to create a mapping function here where it takes in values and the file name. I'm going to open the file name, and I'm going to take for each value and position, I'm going to loop through and enumerate all the unique values from that file. For the value and position in each one of those, I'm going to write out the value and the location for that, the index. I'm going to return the value ID out of this function. So let's see how that works. So I'm going to take my data frame, I'm going to read in the file we just created above with our raw data. I'm going to have no header, and we're going to give these names to our columns, visitor ID, content ID, and rating. And we're going to give the data types. We're going to say this is a string, content ID is a string, and rating is going to be a float between 0 and 1. Next, what we're going to do is we're going to say toCSV. Now we're going to be writing it back out. All right, so we're going to take our data frame that we just created, and we're going to call the toCSV method on it, and write back out to make sure that it has the correct things. Next, we're going to take the user mapping, and we're going to create a mapping from that using our function above, right here. And we're going to map visitor ID to our users. Likewise, we're going to create an item mapping where we're going to take our data frame with content ID and then create our items. All right, let's see what that looks like. So we're going to take the head, the top 3 rows, from each of our data sets that we created. So here's our raw data set. As you can see, here's our long integers for each visitor ID, our long integer for each content ID, and our ratings that go from 0 to 1. If we look at our items file, you can see here is our item, our content ID, and the associated item ID that we created from that. So content ID, item ID, content ID, item ID, content ID, item ID. This is our mapping from content ID to item ID. Let's look at our users file. You can see our user, our visitor ID right here, and then this gets mapped to a user ID. Visitor ID, user ID, visitor ID, user ID. So this is our mapping from visitor ID to user ID. Great. So now what we're going to do is we're going to create a data frame where we're going to take this map and we're going to do the conversion. So we'll take visitor ID, we're going to map it using the mapping we just created, and that will become our user ID in our data frame. Likewise, we'll do the same with content ID, where we map using our item mapping we created to get our data frame column of item ID. We're going to create a mapped data frame now that's going to be the concatenation of these data frames using user ID, item ID, and rating. We're now going to write this out to a file using the method toCSV of our map data frame to the Colab mapped.csv. Let's look at what some of that looks like. Here we go. As you can see in this table, we have our user IDs, our item IDs, and our ratings. You can see these look like matrices. They start from 0, and they enumerate out to n-1 rows, and start from 0 and enumerate out to n-1 columns. And all of our ratings are nicely between 0 and 1. All right, let's see what we do next. Creating rows and columns data sets. All right, so now we have our user mappings and our item mappings. Let's see how we can create our actual data to go to the estimator. So we're going to import pandas and NumPy again, and we're going to read in our mapped data frame. We're going to do that from our Colab mapped.csv file. And these will be the names of our columns: user ID, item ID, and rating. As you can see above, this is what matches. So great. We need to figure out how many items and users we're going to have. So to do that, since everything's enumerated nicely, we can just do a max. So to do that, we're going to take our map data frame item ID, take the NumPy max of that, and just add 1. Because remember, it's n-1 since they're indices. Same goes for users. We'll take the mapped data frame's user ID column, find the NumPy max of that, add 1, and that's the number of users. What we'll do then is we're going to round the map data frame rating to values of 2 significant figures. And let's save that back into our rating. So that way we don't have long, super long floats. Next, we'll print the items and users and interactions, and we'll see what that number is. So we had in this data set 5,668 items, 82,802 users, and between all of those, there was 278,913 interactions. Wow, that's a lot. But still, if you do the Cartesian product between items and users, this is a really small percentage of that. So as you can see, our user-item interaction data is very sparse, like most recommendation collaborative filtering systems have. So now we're going to group by items. To do that, we're going to take our map data frame, we're going to group by the item ID field. Okay? We're then going to create a loop here so we can just see what's inside. And for each item and group inside group by items, we're going to print it out. And we're going to do that 5 times. So here we go. We have the very first one. Here is our item ID, and item ID has 0 has this user ID, and it has this rating. Item ID 1 has user ID 1 going with it, and it has 1 rating. Now, here's where it gets a little different. Item ID 2 has actually 2 users that have interacted with it, user 2 and user 3. And they each had their corresponding ratings right here. So 0.17 goes with this user, and 0.25 goes with this user. All right. Moving on, we have item 3 with user 4 with a rating of this, 0.05, and so on. All right. So now that we have our maps, we need to put this into TF records, remember. So let's see how this goes. So we're going to import TensorFlow in case we haven't already done it. We're going to do our group by items where we're taking our map by data frame, and we're going to group by item ID. Okay? We're then going to call TF record writer for our Python IO stream, and it's going to be users for item. So it's going to be a singular item, a unique item, and all the users that went with that item and all the corresponding ratings that went with those users. Okay? So for each item and grouped entity in there, we're going to loop over them, and we're going to create an example. Okay? So it'll be tf.train.example, and we're going to set our features. Our features are going to be these train features. It's going to be a feature dictionary. Now, if you remember from before, we're going to have 3 things here. We have the key. The key here is going to be the item ID here, item. The indices here are going to be our user IDs that we're grouped by. And the values here will be the corresponding ratings that went with those users. From there, we're going to serialize that all to a string and write it out to the file. Likewise, we'll do the same with users. We're going to take our mapped by data frame and group by, this time, user ID. From here, we're once again going to create a TF record writer, but now we're going to be writing out to the file items for user. So in this case, we have one unique user with multiple items, and then the corresponding ratings that go along with those. Just like before, except now we're going to be looping by item. We're going to loop over item or user, and going to group by those. We'll once again create an example, and this time we're going to have key will be our user ID, the indices will be our grouped by item IDs, and our values will be our grouped by ratings that correspond with those item IDs. Once again, we're going to serialize those to string. To make things a little simpler, we're going to create a sample data set here. We're going to do the same thing, items for user, but it's going to be a subset. Okay, since we have a lot of users, 82,000, remember? So we're going to do this, and now we're just going to loop over the top 20. Now, let's see what our data looks like. So you can see we have lots of files we've created now. We have our raw file here, our users and items mappings, our mapped raw data, and then our users for item, our items for user, and our items for user subset TF records. Great. So as you can see here, to summarize, we created the following data files from ColabRaw.csv. We have ColabMap.csv, which is essentially the same data as in Colab Raw, except that visitor ID and content ID, which are business specific, have been mapped now to user ID and item ID, which are enumerated in 0 to the number of mappings that are stored in items.csv and users.csv, so we can use these during inference. Users for item contains all the user ratings for each item in TF record example format, and items for user contains all the item ratings for each user in TF example format as well. Now that we have our data in the correct format, let's train with WALS. Once you have the data set, do matrix factorization with WALS using the matrix factorization estimator in the contrib directory. It's an estimator model, so it should be relatively familiar. As usual, we write an input function to provide the data to the model, and then create the estimator to do the train and evaluate. Because it's contrib and hasn't moved over to TF estimator yet, we use tf.contrib.learn.experiment to handle the training loop. And then we'll use learn runner to actually run the experiment. So first, to do this, we're going to import all of our libraries. Here you can see we're importing our WALS matrix factorization from the contrib library under factorizations. To do this, we're going to do our read data set, where we're going to pass in the mode, so this is training or evaluation, and then the arguments that are going to be passed. So here's our decode example function that takes our example protos from the TF records and our vocabulary size. Here in the lab portion, you had to fill this out. Let's go over this to see if you did it correctly. So we're going to read in a features dictionary here, coming from our protos. So we're going to have a key here, which are going to be depending on our user ID or item ID, depending on what TF record it's reading. This will be a fixed length feature. The indices here and the values will both be variable length features, and they'll both be the same length. If key is our user ID, the indices will be our item IDs and their corresponding ratings. If key is the other way around, it'll be the opposite. Then what we're going to do is we're going to parse our features using this dictionary we created here from our protos, and we'll get our parsed features. From there, we're going to pull our values out by doing a tf.sparseMerge, which will take our indices and our values, and using our vocab size, it'll create a sparse tensor. And remember, to fix the batching reindexing problem, we're going to save a key to remap after batching. So we're going to take our parsed features key and write that out to this tensor here. Finally, we're going to create our decoded sparse tensor, which will be, first, the indices part of our sparse tensor will be the concatenation of our values.indices and then the key. Because remember, this is how we're going to transfer our key through the input function. And along the axis 0. Our values will be the concatenation of the actual values we've read in, and we're going to add in a dummy value, which will be 0. Lastly, our dense shapes will be just the dense shape we started with. From there, we're going to return our decoded sparse tensor onto the rest of the input function. Now, what we're going to do next is remap the keys from the sparse tensor. Now remember, the reason we're doing this is because the input function during batching replaced the actual key indices that are the first dimension of our indices of the sparse tensor with the batch indices, which we don't want, because during training, you're not going to be able to sweep correctly and it will not actually learn much, because the indices will keep getting repeated every batch, 0, 1, 2, however much your batch size is. So let's see how remap keys works. So we've already covered this in depth, but let's just go through this quickly. So first what we're going to do is we're going to take our sparse tensor that comes in. Remember, this has already been batched, so we have a batch of these coming in. So we're going to have current indices of our sparse tensor that we need to fix. So we're going to write these out, the bad indices and the bad values, which will come from our indices and our values members of our sparse tensor. We're going to group by the batch indices and get the count for each. So for this, all we're doing is basically taking a segment sum, where our data is going to be ones of where our bad indices are, and the segment IDs of our bad indices, and then we're going to do -1. That'll be the size. The length of the batch indices, it'd basically be batch size, unless it was a partially full batch, will just be this. We take the shape of our size, and we'll take just the first dimension of that, and that'll be our length. Next, we'll find the cumulative sum, which will be used for indexing later, right here. Just take cum sum of the size, and then it'll find us our cumulative sum, so we can find our offsets. And to find the offsets, we're going to first create a length range. So we're just going to basically enumerate from 0 to the length, so the number of examples in each batch to find this. And then our indices will be the cumulative range, so we'll just take this cumulative, which are our offsets, plus this, which will give our actual indices of the items we added during the concatenation in our decode example function. From there, we're going to gather. So the keys that we've extracted back out of our concatenated sparse tensor. Okay, so we're going to do a tf.squeeze, gather, using the bad indices. We're going to pull out of those, we're going to extract from it using this gather from the cumulative range of the second column. Okay. So the enumerated row indices, the sparse tensor's indices member, are what we're going to get next. From here, we're just going to create a range. We're going to enumerate over the shape. So that way we have the number of times each example was in the batch. We want to find here the row indices of the sparse tensor's indices member that are of the actual data and not the concatenated rows. So we want to find the intersection of the two sets and then take the opposite of that. So to do that, we're just going to create two little helper tensors here, x and s. X will be our sparse indices range, and s will be the cumulative range. So first, what we've got to do is get to tile this. So we need to know the number of times we're going to be tiling. To do that, we're going to concatenate a bunch of ones using the shape of our tensor, and then the other shape of our S tensor here, cumulative range. We're going to concatenate those two things together, and that'll be the number of multiples that we're going to tile x. So now we're going to expand x, our sparse indices range, into a rank 2 tensor, and then you're going to multiply it by the rows by 1, so there's no copying, and the columns by the number of examples in the batch. So to do that, we just do tf.tile, and then tf.expand dims. We're going to turn this into a matrix, and then we're going to tile the number of times we just found. From there, essentially what we're going to do is a vectorized logical OR, and then we're going to negate it with our unary complement operator right here with this tilde. To do that, we're going to do equal where x tile equals s. So basically here, anywhere that the actual concatenated indice is found will be a true, and then across all of them, we're going to do a reduce any. So wherever there's any trues, they'll all overlap, and we'll get all the trues wherever there is a 1, and then the rest will be left with zeros. And then we'll take a not here with this tilde, which basically flips all the 1s to zeros and all the zeros to 1s. And this will be x not in s. Moving on, the sparse tensor's indices that are our actual data by using the Boolean mask we just made above apply to the entire indices member of our sparse tensor. So now we want to pull out our selected indices here. To do that, now that we have this Boolean mask, we can apply a Boolean mask to it, where our tensor will be the bad indices, and our mask will be this x not in s. And we'll do it along our 0th axis. Now that's the indices, but we also want to get the values, our ratings. To do that, we're going to take the same Boolean mask and now apply it to the bad values tensor using our mask we created along the 0th axis. Now, that's great and all, but we haven't removed the batch indices yet. So first, to do that, we need to replace the first column of our selected indices with the keys. So we first need to tile our gathered indices. So first, we're going to create a tiling. Now, we can't do this as simple as before because the arrays are going to be jagged. Each item might have different numbers of users, and likewise, each user might have different numbers of items. Right? One user might have seen 5 things, and another user might have seen 10. So there's no nice way to do this without a while loop, which we'll get to next. So first, we need to initialize our while loop with an initial tiling. To do that, we're just going to take our gathered indices. The 0th column, these are our batch indices, and we're going to do it multiple times using the size here. OK, from there, we're going to create a loop body. So that way, we can create our own tf.map function, because the stacking of tensor arrays have to be rectangular. And in this case, since they're jagged, we don't have that. So we'll create our own. So to do that loop body, we're going to pass in our loop variable here, I, and then our tensor that we're going to grow here, called tensor grow. Inside the loop body, we're going to return the next loop variable, so I plus 1, And we're going to concatenate our values here, which are going to be our original TensorGrow, and then we're going to add on top of that a tiling of that of our expanded DIMs of our gathered indices. And how many times we're going to do this? A multiple number of times that we found above based on the size. How many items that user had, for instance. Well, that's great and all, but we need to call this loop. So what we're going to do here is we're going to create our tf.while loop, passing in our lambda of our loop variable here and TensorGrow with a condition that I is going to be less than the length, because we don't want to go outside of our batch. And then we're going to have our loop body, which we're going to execute. And then we're going to pass in our initial variables for I in TensorGrow, which will be 1 for I, and then our initial tiling for TensorGrow. This will get us our result tensor here. So now what we're going to do is we're going to concatenate our tiled keys with the second column of selected indices. Okay, so that way we'll have the correct keys now. So selected indices fixed will be the concatenation of expanded DIMs of result, because right now it's a vector, so we're going to turn it into a matrix. And then we're going to concatenate that with the expanded is the selected indices of the second column. Because remember, we don't want the first column, because the first column is the batch indices, which is what we're trying to throw out. So we want to get these. And we're going to concatenate those two together along columns. Now that's all fixed, we've got to put it all back together in a nice sparse tensor so that our input function can send it off to the estimator. To do that, we're going to create a sparse tensor using our indices, which will be our selected indices fixed, and our values, our selected values. These are our ratings right here. And the dense shape will be the same as before. And then we return back out to our main parse TF records function. So now we're going to parse TF records, where we pass a file name and our vocab size. So if mode equals train, we want to make sure that the number of epochs equals none. So that way it trains indefinitely and uses the train steps to decide when to stop training. Else, if we're not in train, in other words, evaluation, we're going to have one epoch so that we just go through the dataset one and only one time, and that way we can do our evaluation correctly. What we're going to do here is get our files list. So we're going to take our input path from above using our file name, and we're going to create a list of files in case the files are sharded out because it was too big for one file. From there, we're going to take our file list and create a data set. To do that, remember these are TF records, we're going to create our TF record file data set using our files and create our data set. From there, we have to do our decode example function that we just went through above using our example protos as input and the correct vocab size depending if we're doing items or users. Next, we're going to repeat the number of epochs that we set up here. Next, we're going to do our batching. So we have a batch size number of items or users depending on which phase we're in. But here we're going to do our remap keys to fix some of the batching indices being overridden. And lastly, we're going to create our one-shot iterator, which will return our batch of examples. So now this all gets called in our wrapped input function right here, where we create our features dictionary of input rows, where we call parse TF records for items for user. So remember, this is a single user having multiple items and therefore multiple ratings. And the vocabulary here is the number of items. And then our input columns for our factorization is going to be using the users for item file, where now our vocabulary is the number of users, where we have one unique item and multiple users for each item, and therefore also multiple ratings. Lastly, we're going to have project row here, so that way we can use this during serving, where we can just decide are we predicting rows or columns. So true will predict rows, so we'll be predicting items for users, and false will be predicting columns, so we'll be trying to predict users for items, as in like a targeting model. From here, we're going to return features and none. Remember, this none here is usually for our labels. But because this is an alternating algorithm, in the one phase, our labels are going to be the columns, and the other phase, our labels will be the rows, because we fixed one while solving for the other, and vice versa. And just for developing line by line, you don't really need this in production, but just so we can see, we're going to create an input function subset, where we just use our small number of users we created here out of the 82,000. All right, and then from there, our input function's done. Let's try it out and see what it looks like. So this code is helpful in developing the input function. You don't need it in production, but it's a good way to check while you're coding to make sure things are running smoothly. Okay? To do this, we create a function called tryout. And to do that, we're going to create a session. Within that session, we're going to create a function that's going to point to our read dataset function above. And here we're going to pass in our mode. Our mode is going to be eval in this case. We're going to be reading from the eval dataset. And we're going to do our input path, our data, and our batch size is going to be 8. Our number of items is going to be 560, 68. And our number of users is going to be the total number of users, 82, 802. We're going to write out our features from this function as we call it, and then we're going to print off our features, our input rows, using the eval. Let's see what that looks like. As you can see, we have our sparse tensor. Here are our indices. Okay. You can see these are going to be using our input rows here. So that means that these will be user IDs, and then these will be item IDs down here. And then here in our values array, these are the associated ratings that go with each of these combinations, these user item combinations. And of course, our dense shape is going to be the batch size here times the number of items. All right, so now that's great. Let's set up our function to find the top k. Because we don't want every single recommendation for every single user. We just want the top k of them. To do that, we're going to pass in the user ID, the item factors that we've been trained, and then what k should be. Should it be 5, 10? It all depends on what your problem is. All right, to do this, we're going to get all of our items. We'll solve the entire matrix by doing a matrix multiply of our user, expanding dims into a 1 by number of user vectors. If it's just one user, just be 1 by 1, since it's not batch prediction yet. And then we're going to do a transpose of our item factors, which will be a items by k or d-dimensional matrix. To get our top k, we're going to do tf.nn.topk of all of our items, where k equals k. And then lastly, we're going to return the casting of the indices to integers, because remember, these are supposed to be IDs, so we're going to pass those IDs back of the top k items. But if you want to do more than one at a time, one user at a time, you should do batch prediction. So here we're going to pass our arguments. Inside, we're going to call numpy, and we're going to create a session. Remember, this session is a completely disconnected graph. It's its own graph running its own session. To do that, we have to create an estimator. This estimator will read in what we've already trained from our output directory here, from intermodel directory, so that we can read in the values that were trained and get our user factors and our item factors to be able to do our predictions. So we're going to call our estimator here, which you should have filled in during the lab, of tf.contrib.factorization.walls matrix factorization. Our number of rows will be, of course, the number of users. Number of columns will be the number of items. The embedding dimension, this is what we decided how many latent features we would solve for. It's going to be number of embeds. And here's our model directory. The rest of the lab was already done for you. So now you can kind of just follow along and see what we've done. So this is how you get the row factors for an out-of-vocab user data. So if in case there was a new user or a new item, you could use these. So you do a list, you get projections, using that, and you convert to a tensor of the row factors. But for in-vocab data, so for users that already exist and items that already exist, we can use this instead. So the row factors are already in that checkpoint. So user factors would just be a tf.convert to tensor. You're going to call the estimator, and you're going to call the method getRowFactors. And you're going to get the first dimension of that, which will be the number of users by number of embeds. Will be the shape. In either case, we have to assume the catalog doesn't change. So you have to assume there's been no new items added to the interaction matrix. So column factors are read in. So item factors will just be tf.convert to tensor. We're going to once again call our estimator using the method getCallFactors, taking the first dimension, and it's going to be number of items by number of embeds as the shape. For each user in our batch, we're going to find the top k items. So top k is going to be a squeeze. We're going to call this map function to be able to loop through all these users essentially with this vectorized top k. I'm going to do user. I'm going to call top k using user, where user factors will be our elements that will loop over, and then our item factors will be what we multiply with, and then our top k will be how many we save back out, and that gets written into our top k right here, which will be users by top k shape. From here, what we're going to do is we're going to create our batch predictions. Okay, so for the best items for a user in top k, we're going to evaluate this tensor right here, this top k tensor. From there, it runs the graph, and then we're going to write out a comma delimited list inside of our file name here for each unique user, what their top k items would be. How do we call this? Well, we're going to create our serving input function that we're going to pass arguments to. For user embeddings, where we pass a user ID, so all items for this user for the user embeddings, the items will be a range, an enumerated range of all the items possible. The users will be the user ID times a tensor of ones for all the items. So that way, essentially, we tile their user ID across all of them. The ratings will just be a dummy right now, 0.1 times the ones like the users, So this should just be used because we're not actually using the ratings. We're predicting ratings. But we need a placeholder right now to be able to write into. Then we'll return our items, our users, our ratings, and our TF constant true. Does anyone remember what TF.constant true is for? Remember, this was our project rows. Since we're predicting for users, we want to have this be true. Whereas if we're predicting for items, it would be false, as we'll see shortly. If we're doing it for item embeddings, where we pass in the item ID, the users now will be the range, the enumerated range of all the users. And the items ID will now be the item ID tiled across all of the ones for each user. The ratings once again will be dummies, and we're going to return the items, the users, the ratings, and now false, because now we're projecting columns and not rows. All right, so now this all gets called in the serving input function. So we have a feature placeholder where we read in data from whatever is sending the inputs to our model. We have a placeholder for one integer for a user ID and one integer for an item ID. In here, what we're going to do is we're going to say, well, depending on what's sent, we have to make sure we're either doing users or items for what the user that sent this request wants. To do that, as we mentioned earlier, we're going to use a tf.cond, where we're going to see if the user ID is less than 0, so if they give a negative number, we're going to do item embeddings instead. Else, if it's greater than or equal to 0, we're going to do user embeddings. To do that, once we're done figuring out if it's for items or for users, we're going to stack the users and items tensors together to get our rows, and then we're going to do the transpose of stacking the items and users tensors together to get the columns. From there, our input rows will be a sparse tensor of the rows with the ratings as our values, with the dense shape of number of users by number of items. Our input columns will be the transpose by using the columns as our indices now and the ratings as our values. Once again, with the dense shape of number of users by number of items. So now we have our features dictionary we're going to create from these placeholders using input rows, input columns, and what project row is. Lastly, what we do, we return tf.contrib.learn.input function ops, our features, no labels, and our feature placeholder. And we return our serving input function. Wow, that was a lot, but we finally made it to our train and evaluate function. First, what we got to do is figure out how many training steps we're going to do. To do this, we can do a little bit of math and figure out maybe the number of epochs, also times the number of users, times maybe add 0.5, and then divide by the batch size. That might be a good number of train steps to perform. And the steps in each epoch might be 0.5 plus the number of users divided by the batch size. So this will tell us that we're going to train for this many steps and evaluate this many times. So now we're going to create our experiment function that will write out to our output directory. It's going to return an experiment, and inside the experiment is going to be our estimator, which will be the tf.contrib.factorization.walls matrix factorization, where the arguments we're going to pass, the number of rows will be our number of users, the number of columns will be our number of items, the embedding dimension is going to be the number of embedding dimensions we want, so how many latent features are we shooting for here? Is it 2, 4, 20? And in our model directory, which is where we're going to write this all out to keep our model files. Our train input function will be read dataset, where we pass in the train keys, so that way we're going to use this mode to make sure that our number of epochs is none, so it'll indefinitely run until we run out of train steps. And our eval input function will be the read dataset, except now with the eval, so we'll run through the dataset only once, because number of epochs equals 1. Our train steps is going to equal our train steps from above. Eval steps is going to equal 1. And then our min eval frequency will be the number of steps for each epoch that we're going to do, that we set up here. Now we also want to save this model out, so we're going to define an export strategy here using our saved model export utils. We're going to make that export strategy our serving input function. It's going to be our create serving input function with our arguments passed to this train and evaluate function. From there, we're going to import tensorflow.contrib.learn.python.learn the learn runner. This learn runner is actually when we run our train and evaluate loop. As you can see here, learn runner, it's going to run our experiment function, and it's going to write it out to the output directory. And then after we're all done with that, we'll do a batch prediction using our arguments. From there, we're going to import our shell utility here, and we're going to call that with the method remove tree, so that way walls trained will be completely fresh. So that way when we train into it, we won't have any collisions or any problems. It'll be exactly this run. Now we're going to pass our arguments. We're going to create a dictionary here. Our output directory will be called walls trained. Our input path will be data. And remember, we have multiple data files in there. Our number of epochs will be 0.5 in this case. Number of items is going to be the number of items that we found. The number of users will be the number of users we found. Our batch size we chose to be 512. Number of embeddings is going to be 10. So there'll be 10 latent features in this model. And then our top k is going to be 3. Of course, you can always change these things down here because they're hyperparameters. All right, so as we can see, it'll train. In this case, it's going to train for 8 steps. It's going to evaluate every 161 steps. To do that, it's going to create our train and evaluate loop. It's going to create our checkpoints, all of our configurations, and then it's going to start running right here. It starts running, starts doing its training, it's doing its sweeps, it's saving out checkpoints with our models here. Here's our loss function right here. So we got 97,000 loss for the first step. It's going to fit the step starting, going on, saving checkpoints now for step 8, which is the last step, remember, because we're doing 8 steps for training. And then it writes it all out. Here's our loss for our final step. And then we're done. And then we do an evaluation. And here's our, for step 8, we're at step 8, and this was our loss at evaluation. And then we're done with that part. So now, if we look at what's inside our Walls train directory, we can see we have batch prediction.txt, our checkpoints, the evaluation folder, the events out, so we can look at this on TensorBoard, the export, this is where our saved model is trained, our graph, and a bunch of checkpoints that it's made. Let's have a look inside batch predict.txt. As you can see here, we have our, for each user, our top 3 movies. Isn't that great? However, you might notice that these are not our original content IDs, which we'll talk about later. We need to maybe do a reverse mapping to get these back into the content IDs we care about. So you can also do the same by running it as a Python module. So here, everything's basically the same except it's been copied into a model.py and a task.py, where we pass on by command line the parameters that we care about. As you can see here, it trains as it did before, except now using the module. And it writes the saved model out to where we pointed to. And then we're done. Now, if you want to get row and column factors, you need to do a little bit more. So once you have a trained Walls model, you can get row and column factors, user and item embeddings, using the serving input function that we exported in our export folder. We'll look at how to use these in the section on building a recommendation system using deep neural networks in the next module. So as you can see here, we're going to create a input JSON. We're going to have a user ID. It's going to be 4, index 4, and item ID, index -1. So what this means is we're going to be predicting items for a user, since this is -1 and user ID is positive. So our tf.con will say, oh, this is users I'm doing here, not items. To do that, we're going to send in our input JSON, and it's going to do a projection out of these are the items that are the best for the user. Their ratings, the predicted ratings. Same goes for the user ID. We're predicting for item 4 now, so now we want to target users for that item. So we're going to send that off to our ML engine local predict, and once again, we're going to get the projected ratings for those. So now to run on cloud, we do the same exact thing, but first we're going to send our data to our bucket on Google Cloud Storage in Walls data directory. Next, we're going to call the cloud training job. That'll use our module that we created and send all that over using a basic GPU. And using our number of epochs now at 10, because now we have the power of the cloud behind us, so we can definitely go a lot bigger and larger, and our number of items and number of users. And we send that off, and it takes about 10 minutes or so for me. We'll see how it goes for you. And that's that. That's the Walls Matrix Factorization Lab.